Alright, so everybody welcome to binarysearch.com. They will upsolve weekly contest 57, and if you tried to participate in it yesterday, then you probably know that the contest got delayed first and then it got cancelled. So unfortunately we were not able to participate live in it because there was no live contest, right? So that's why today I created a custom room. I handpicked the questions that were supposed to go into that contest. I believe they will be in the correct order, but let's see. So yeah, I tried as much as I could not to spoil the questions to myself. I believe I succeeded, so I've seen the names of the problems, but not more than that. So let's go and see how it goes. Because it's of course not an official contest, we can spend much more time explaining things, so hopefully it will be a better content actually. Let's start. First problem is validate delivery orders. So we are given a list of strings orders. Each element in order starts with either P meaning to pick up the order or D meaning to deliver it, followed by the order ID. For example, P12 means pick up order 12. Okay. So return whether orders is valid given the following rules. A delivery cannot happen for an order before pickup, very reasonable. Every pickup must be delivered. An order that's already been picked up and delivered cannot be picked up or delivered again. Makes sense. So I believe what we can do is create a set of active pickups. So it will be a set, and for every order in orders we can do the following. So first we want to know if it's a pickup or a delivery. So is pickup gets order 0 equal to P, right? Because if it's P then it's pickup, if it's not P then it's delivery. Then we also want order ID, which will be like everything but the first character, and then we want to convert it to integers because it's an ID. We may actually ignore this conversion to integers, but let's keep things in the type they should be in. So if our order is a pickup, and we also want a set of closed pickups. So if an order is a pickup, we want to check that it has not been closed already, because if it was, then we can just return false straight away. Else, although else it's not necessary here, but let's write it for consistency. Else we want to add this pickup, to add this order ID to active pickups. Otherwise, and I believe that this thing we can just do straight away, right? Like, no matter whether it's a delivery or a pickup, we cannot process it if it's closed. And I believe active and closed it's better just active and closed, because active orders and closed orders, right? You don't actually think of an order as only a pickup. It's not an active pickup, the pickup has already happened, and now we are just closing the order itself. These variable names are a bit more reasonable. Otherwise we want to add it, yeah, of course, we want to add it to closed orders, and remove it. Remove, I believe, is the name of the method. Now you see, like, an if idea would be just to return true, but there are more problems. Like, actually here I assume that order ID is inactive, right? So else I should state it explicitly. If our order ID is active, then we can do something, right? But if it's not inactive, if it, like, we are trying to deliver in order which we hadn't picked up yet. So then we should just return false. And I believe we can write it like that. Both these cases correspond to a delivery. And then also we have a temporary variable that we only use once, so why not just use it here. But order ID we use a lot, so it's reasonable to have it straight away. But we also want to check that set of active orders is empty. I believe that now we want to return whether it's not active. Let's submit and see if we... Okay. Oh, because we are trying to pick an order twice, which should not happen. That's reasonable. Let me think. Yeah. So if order ID is active, it can't happen. We're trying to pick up the same order twice. Otherwise, we can say it's fully added to active orders. Yeah, I believe this should be it. Alright. Let's check if there are editorials for... Well, picked and delivered, more or less the same thing. You also don't have to cast it to integers. Right. And you can, I believe, true delivered, false to be delivered first time. Yeah, well, that can happen. You can model it with one set or dictionary. Yeah, with one dictionary, but the same thing, more or less. Oh, actually, both guys did a good job, I believe, explaining. Yeah, okay. Which we have delivered. Yeah, looks reasonable. The idea is fairly simple, I agree. Just implement the given rules, kind of brute force. No, it's not. Well, brute force is when you just loop through all possible options, and they call it implementation problem, not brute force problem. And they also have two sets which are unordered, which makes sense. Sets of strings should not be that fast. Actually, no one converted. Okay. I mean, nobody converted order IDs to integers, fortunately. Okay, let's check the second problem. I believe there is not much for us to speak about in the first one. So in problem B, log truncation, we are given a list of integers logs and an integer limit. Each element in logs represents the size of logs generated by user I. A limit represents the total size of logs you can store in your system. Okay, so I originally thought that we have like a physical log of wood and we truncate it, but apparently it's like computer logs, right? Execution logs or something. So we want to return the largest x such that if we truncate every log in logs to be at most size x, the sum of the remaining log size is at most limit. If no log needs to be truncated, return the largest log size. Okay. Well, straightforward idea for that problem is binary search over the answer, because we have a really simple check function. I don't think that we should think more about that problem, we should just implement it. So the idea is, like, if we truncate everything to 0, it's always possible, right? Otherwise, otherwise actually, what is otherwise? Let's say that we, like, if we truncate everything to limit +1, then it's never possible, right? So that we know for sure that we want to return low. Then we write our standard binary search. If we can do something, then we assign middle to left, or to lower, I should say, because our idea is to maintain the invariant that low value is always possible and high value is never possible. I will be just extra careful here, although it's not required. And then we have our check function that will work as follows. We want to truncate every log to be at most middle. So the total size will be as such, although I believe it's minimum of 2, and it should be at most limit. Expected 7, limit 100. I believe we have to say like max logs. Right, that's what we wanted to say, because they said like if we don't have anything to truncate, don't have to truncate anything, then we want to return the max log size. Therefore, max logs +1 is never possible, but max logs is sometimes possible. Yeah, that's kind of silly function. We can just write it here because of Python loop comprehension. I don't know which one is faster actually, there's like almost no difference between them. Oh, and we can do it in a greedy manner, okay. Instead of binary searching the result, we can sort the logs and look for a threshold log size that has to be cut out. Those are largest. But that's like why would you do that? I mean, okay, you sorted logs, and then I completely agree. Oh, because, yeah, okay, that makes sense. That makes sense. Like, we're kind of recomputing, but not really the same thing. We compute that expression, sum of minimums, with a given value. Like, it can be computed more efficiently, but you need a bit more math for this. So yeah, it has a nice property that complexity does not depend on how large numbers can be, but it doesn't really matter because, like, of course, log factors are not always free, but mostly they are free, and in our case, log number of bits in our integers is pretty much reasonable values. We can live with it. Wait, okay. Yeah, it's just our solution, but in C++. I like it because it's our solution. Looks really similar. But don't log n. Okay, no. You have to understand that it's not n log n, but n log max value of integer instead. Do we have bounds on limit? No, we don't. Okay, so it's not. Again, times. No. So both actually are wrong. Because, yeah, when you binary search, your complexity is logarithm of the search space. And the search space is from 0 to 2 to the power of 31 minus 1, potentially. I also wonder, like, how did it happen so that it passes? Why would that be invalid? Limit is less than 2 to the power of 31. Okay, what if I just say like 1 over 4? Oh, because here we are, okay, but still very, very questionable. Let me see what. 0, 0, 0, 0, 1 more 0 here. Okay, so this is very implicit, I don't like it. The statement clearly should contain that locks can't overflow, although it sounds more like outer solution can't overflow is the actual constraint, which is not very nice. So how we can. The description is confusing or incorrect, I believe. What kinds of overflow will not happen? It's like it's vague on my side, actually. Kinds. I believe this is this is better. Okay. But still we have like this very similar to this. But actually this was posted before this, right? 18 hours ago and 17 hours ago. So this was the first one. Check all middle values, so time complexity makes element, find the same. Is what? Is word lengths, word widths? I don't remember exactly how they call it. Yeah, word lengths. Is a word length. Okay. Yeah, basically this comment can apply to all 3 solutions. Yeah. Actually, there's like technically there's nothing bad about this editorial, but like we already have 2 editorials that look exactly the same. Although this one has a separate function. No, this is really bad. Like, yeah. You see? Yeah, I'm pretty sure that if we just check this solution, so okay, I don't know how is that fast. If you take by reference, it should be faster, right? Well, okay, it doesn't really matter in this particular context because test cases are small apparently. But yeah, I just, this was just wrong. Okay, we will not download anything, although it's kind of duplicate, but okay, let's first solve all problems and then maybe we'll write an editorial. Because there was no editorial in Python for like binary search over the answer. Right. Okay, problem 3, brick layout. We are given a list of integers bricks and integers width and height. Each bricks I represents a 1 times brick size brick. We want to return the number of ways to lay the bricks such that we get full layout of bricks with width and height. Bricks can be reused, but can only be laid horizontally. Okay. Okay, but then like it's the same thing as number of ways to fill a row, and then to the power of number of rows, which is height, and then number, and okay, so and then we want to compute something. Number of bricks, we have 1000 bricks and width times n. Okay, that's a clear dynamic programming constraint. But either way, we want to return this to the power of height. And because we're using this, yeah, ways. So we'll count how many ways there are to fill all strips of length up to width. Because what we can do then is the following. So for what is it? Length in range width for brick in bricks. I believe bricks are not unique apparently. Like bricks can be reused, but we'll still give you duplicate bricks. Well done, well done. Like, what was the point of that? Okay, it doesn't matter. So if lens minus brick is greater than or equal to 0, ways at lens plus equals ways at lens minus brick. It should start from 1, and then we can do this. List index out of French because, of course, I forgot to do this. Wait, so they are all different? They have the same lens, but they are different. Okay, whatever. Dynamic programming with basically the same solution, although written in a bit different way. JavaScript, I had a fun time apparently. Or had nothing to do, I should say. We have... Well, that's good, that's good. Yeah, pretty much everyone wrote the same thing, but I don't know, we cannot, we can, so it's 11, 12, and 1102. Okay, I prefer the earliest solution among any two, but it's the same thing, basically. Okay, let's check the last problem. So here we just to make it clear, we computed the number of ways with dynamic programming to fill one row. Because rows are independent, we will just use the combinatorial product rule, which says basically multiplies the number of ways you have to fill each row. And when you multiply the same number again the same as exponentiation to the power of number of rows, which is height. And this part, I believe, can be done in a faster way. I believe it has something to do with Fourier transform, fast Fourier transform, but I'm not sure. I'll just check problem 4. We are given the first line, of course. So we are given two-dimensional list of integers, routes, and countries, as well as integers start and end. Each element in routes contains x, y weight, meaning that to travel from city X to Y costs weight. What weight does it cost? Do we pay in gold and therefore the cost is weight? Or what happened here? So each element countries I represents all of the cities that belong to country I. Every city belongs to exactly one country. This is how it works, yes. We are currently in city start and want to travel to city end. During this trip you want to minimize country-to-country border hubs as the first priority and then minimize total weight. Return a list of two elements worth of... so basically it's Dijkstra, but the distance is a tuple. Okay. Why not? The first thing we'll need to do is create a dictionary which can quickly give us a country ID of a given city, because current format is not very well suited for this purpose. So what we should do is say like something, country ID of city equals country. Wait, Countries I represents all cities that belong to country I's. We have country and then cities, right? In enumerate countries. And then for city, in city, for every city of that country, we want to say the country ID of that city country. Okay, and then apparently it's a Dijkstra. Can send the resolution. Wait, needed to make a trip. Okay. So what we have is distance, which we don't have anything clear. No. Okay. Okay. We also wanted a graph, I should say, which is default dict list. Default dict and infinity, because no, actually default distance infinity. For source destination, are the routes bidirectional? It's unclear. No, exactly. Actually, here. The rods. Oh, excuse me. Did it work? Okay, I will just save it for later. So for source destination weight in rods, graph source pens. Actually, no, it should be dict. Does it matter? No, it doesn't matter. Okay, I was wrong. Destination and then weight. So we create a graph, we create country IDs, distance at start should get 0, 0. And the very end we want to return distance ends, I assume. 0, 0 start. So borders, weight, and then city, so here we just write our usual Dijkstra, right? We pop the minimum element from the heap and we say for neighbor and weight in graph of that city if country ID of neighbor is different from country ID of city, number of borders gets incremented by 1. Total weight, we can, no, we can't. Yeah, I'm stupid. We don't want to do this. So here, if borders plus 1, total weight plus weight is less than distance neighbor, distance neighbor should get that value, and Dijkstra, we should push each tuple consistent of this in neighbor. Otherwise, we just don't increment the number of borders if the country ID is the same. Okay, it worked. I see a Python solution. D plus V. No, that's dirty hacks. You don't want to write code like this because it may fail like for large values. What is this? No. I mean, it doesn't even mention what's... No, not like this. It's well known that you can find shortest path. Okay, what's our... Resources. What's our... Yeah, no, it's fair play. Although... No, this one was posted clearly later in this one. And then we have... No, I don't like this. Wait, this used the same technique? No, it used pairs. Like normal people use pairs because you can put pairs into priority queue, I believe. Wait, queue? How did we? This is some smart version of Dijkstra that I don't understand. But apparently it works. Wow. Okay, really cool. I believe this is why we needed that resource, okay. The idea is, well, no, we already read that one and we disagree. Like, this is not the way you want to construct your cost function. Use priority queue to speed up implementation. Also, hash pool. 0, 0, yeah, like just like normal people, we... Yeah, that's basically what you want. Yeah, and that's also tuples of integers. I agree. But this is, I don't feel like this one is good. Okay, maybe we can... Like you see, we're using these two guys a lot. Maybe we can simplify. Actually, we can use just this, but here we will add 1 if they differ. Why is it useful? Because it allows us to write code in the same manner. If new distance is less than distance, distance gets new distance, and here we want this. Yeah, but it's fairly slow because of this, I suppose. No? Okay. But yeah, of course, I just don't like this code duplication. This looks strange. I don't know. Yeah, we probably need that like normal solution for this one. Does it fit? Yeah, it's fine. Okay, well, if you don't want to see me writing editorials on stream, or I mean, in the video, right? Like, so as for solutions to solve for today, it's been pretty easy. Even with, we took like a lot of time to explain things, and we still solved everything in sort of 5 minutes. So probably, if we just were solving problems, we would solve everything like in under 20 minutes for sure. So yeah, hope these solutions helped you in case you missed the contest or didn't know that there are new problems. So that's basically it for today, and actually, if we don't have contests tomorrow, I may catch up with lead code contests. I will try this week's weekly or bi-weekly, whatever it is, if there are no contests on a work week. And why don't I solve something and just make it useful, right? So stick around for more content, and I'll see you soon. Bye bye.